Alright, so today we will continue our discussion on the C2 scheduling techniques. Last time we talked about two scheduling algorithms. What was the first algorithm that we talked about last time?
First come, first serve?
Yeah. First come, first serve. And what was the other one?
Shortest time first.
Shortest job first. So, what's the problem with first come, first serve?
It has a starvation problem.
A
Starvation problem of processes that have a longer CPU burst time.
Okay. So in fact, first come, first serve does not have a starvation problem.
No.
By definition, first come, first serve does not have a starvation. Why? So it's important to understand this. Yes?
It's like an average waiting time problem.
Yeah, so the average waiting time can be long, but we do not have starvation. Well, who can explain why first come, first serve does not cause any starvation? Yeah.
It doesn't care about the writing time per se, just whichever process requests first will be granted first. It doesn't have any sort of priority.
Yeah, it doesn't have any sort of priority. So what is starvation? What's the definition of starvation? Is it precise to say starvation means waiting for a long time? No, it's not. So strictly speaking, even if a process waits for a long time, that doesn't necessarily mean starvation. Starvation means that you are not setting a limit on the number of other processes that may get the resource while a process is waiting. So if you are waiting, if your process X is waiting, you are not setting a limit on the number of other processes that will be getting the resource while process X is waiting. Now, so it's a limit on, to avoid starvation, or to have a starvation-free system, you need a limit on the number of other processes that will get the resource while one process is waiting. Okay? So it's not a limit on the time, it's the limit on other processes. So basically, if I am number 7 in the queue, and there are 6 other processes, then to avoid starvation, I should wait for 6 processes only. And these 6 processes, it could be that these 6 processes, each one of them gets 4 turns. So it will be perfectly fine to wait for 6 times 4, which is 24. That will still be bounded waiting. As long as there is a bound, as long as there is a limit, there is no starvation. Okay. But when there is no limit, and what's an example? Who can recall an example of starvation that we have seen in one of the synchronization problems that we have studied?
Shortest job first?
What's that?
Shortest job first? Or all the short jobs get...
The synchronization problem, the classical synchronization problems.
Peterson solution.
Hmm?
Was it Peterson solution?
No, because the solution doesn't have starvation. What's the biggest starvation example that we have seen? Yes?
The readers and writers?
Yeah, readers and writers. Yeah. The first solution that we have studied for the readers-writers problem, if readers keep arriving, writers may starve. So if you have a writer waiting and an unlimited number of readers may keep arriving, an unlimited number of readers may keep arriving and getting access to the buffer while a writer is waiting. This is starvation. Starvation means there is no limit on other processes that are getting access to the resource. So with this definition, there is no starvation with shortest first come, first serve, because it's basically queue-based. Whenever you have a queue, whenever you have a first in, first out queue, you will not have starvation. So the problem with first come, first served is the long waiting time. What's the problem with shortest job first? Yeah, starvation. So this is where you may have starvation. Because if you are waiting and you are a process with a relatively long CPU burst, and processes with shorter CPU bursts keep arriving, they will keep getting the CPU and you are waiting. So, and there is no limit. There is no limit on the number of other processes that may keep arriving and getting access to the resource while you are waiting. Okay, so this is the problem with shortest job first. And generally speaking, and I think I have mentioned this last time, starvation is a problem that a certain family of algorithms, of scheduling algorithms, suffer from. Shortest job first is a special case of a more general kind of algorithms that suffer from starvation. And what's that more general?
Is it greed?
Priority?
Yeah, any priority-based algorithm. Any priority-based algorithm. So shortest job first is a priority algorithm, where the priority is the length of the CPU burst. So it's a special case of a priority-based algorithm, and any priority-based algorithm will suffer from starvation because higher priority processes may keep arriving while a low priority process is waiting. Okay? So this is these are the concepts. Now, one more issue about shortest job first. We said last time that to implement shortest job first in a real system, there is a certain difficulty or issue that will face an operating system designer who tries to implement shortest job first in a real system. What's the main challenge?
Knowing the burst time.
Yeah. Knowing the CPU burst time, because we're trying to schedule based on the length of the next CPU burst time. That's what we care about. That's what we are trying to schedule, the next CPU bursts. And the next belongs to the future. And the operating system doesn't know the future. But the operating system knows the history. It knows the past of the process. And based on the past, it may make a reasonable estimate or guess about the future. And this is exactly what we will be studying today, which is one way of estimating the length of the next CPU burst based on the length of previous CPU bursts. So we will be we'll be using this formula. This is what we call the exponential average. So the formula is going to say tau n plus 1 equals alpha tau n plus 1 minus alpha, Tn, 1 minus alpha tau n. So now, what are the meanings of tau and t? Tau is an estimated or calculated, while t is real time, time that is measured or actual. So we're saying here that the length of the next CPU burst may be estimated by calculating a weighted sum of the length of the last CPU burst plus a weighted sum of the length of the last CPU burst and the last estimate. Okay? So now let's see how we do this calculation with alpha equals a half. Now clearly alpha here is a weight that indicates how important or to what extent we want to emphasize the length of the last CPU burst versus the last estimate. Okay? So when alpha is half, then both are equally important. We are giving them the same weight, and the weighted sum is basically the average of the two. So let's look into this example. So the black curve here is the actual behavior of a process, the lengths of the CPU burst. So a process whose first CPU burst had a length of 6, then the next had a length of 4, then the third had a length of 6, then it dropped to 4, then all of a sudden the length of the CPU burst jumped to 13, and then it stayed at 13. Okay? Now we will see how this formula can be used to predict this behavior. So now initially, in the very beginning, before the process starts executing, the system has no idea about the length of the CPU burst. The system has no history, no record of that process. So it must make a guess. So it will just make a guess. You can think of it as a random guess. It will say, okay, the length is going to be 10 time units. A better guess, given that I don't have any history for this process, this guess could be, for example, some average CPU burst length in the system. The system can just, calculate an average of CPU burst lengths, and it will start with this average, average CPU burst length. So it will make a guess, which is 10. Then the process gets its first CPU burst, and it turns out that the length of that burst is 6. So now the system has the last guess, or the last estimate, which is 10, and the latest length, which is 6. So it will calculate a weighted sum. A weighted sum with an alpha of a half is an average. So the average of the two is going to be 8. So now our estimate, our most recent estimate is 8. Then the system is going to look at the length of the next CPU burst, and the process will have a CPU burst of 4. Now again, taking the average of the last measured length, which is 4, and the last estimate, which is 8, and the average of the two is 6. Now our latest estimate is 6. And the next length that the system will measure is going to be a 6. So the average of a 6 and a 6 is a 6. Then the measured length is going to be a 4, so the system will calculate the average of 6 and 4, which is 5. Okay. So the system is basically tracking the lengths of the CPU bursts, and it's calculating this weighted sum. Clearly, at any point in time, this tn, this is a measure. This is one number. This is one measurement. But it's the most recent. However, this is accumulative, right? So this is your guess at time n, and inside of this, you will have tn minus 1 and tn minus 2 and tn minus 3 all the way to t0. So inside of this tau, this is an accumulative history of the process with more recent time, with more recent lengths having higher weights than older lengths. Okay. Yeah.
Once you know enough CPU bursts of, the previous times that a process has been run, why do you still need tau in your formula to guess the next?
Okay, so this is a good question, because trying to to predict the behavior of the process in the future, is it always a good idea to predict the behavior on based on the latest length of the CPU burst. So it's just like trying to predict the performance of a student. Does it make sense to predict the performance of the student on their score in the last test that they have taken? Or it will be a better prediction to take into account some history, the last 10 tests. If my prediction is based on the last 10 tests that the student has taken, this is more likely to be accurate than a prediction based on the latest score that the student got. Maybe the latest score, the student was having some health problems or whatever, and they didn't do well. And I can't predict their behavior based on their latest score. So my latest guess has in it will capture all of these different times with different weights. And this is the most recent. Now, which one should get higher weight? When you give them the same weight, it's balanced. But if you do alpha equals 1, what does this mean? When you set alpha to 1, what are you saying?
The next one's going to be 0.
Hmm?
Is the next one going to be 0? Like the estimate's going to be 0?
The next is going to be 0?
Yeah, the tau would be 0 for that. Or
Tau-
adding 0. You just have alpha times the last measurement.
Yeah,
is
so you're
equal
saying
to
that tau n
prediction.
plus 1 equals alpha Tn. What does this mean? What's the concept here? Conceptual, what does it mean? What are we saying?
Last time.
Same time, twice in a row.
So we are predicting based on the latest length of the CPU burst. It's just like predicting a student's performance based on the last score that they got. And this is unlikely to be a good prediction, because maybe the last CPU burst was unusual. It was unusually long or unusually short, too short or too long. So that's why it's good to have some accumulative history, but more recent history should have a higher weight. So in this formula, we are giving a higher weight to more recent history, and less recent, older history will have lower and lower weights as you calculate more numbers. Because when you expand this formula, you will get something like this. So Tn is multiplied by alpha, but Tn minus 1 is multiplied by alpha times 1 minus alpha. And Tn minus j is multiplied by alpha multiplied by 1 minus alpha power j. So the weight of tau n minus j is much lower, which makes sense. And that's why you will get this blue curve here that is a reasonable approximation of the actual behavior of the process.
Are we not concerned with how alpha actually gets determined?
Sorry, say the question again.
So alpha is used to weight the time measured versus the previous averages, but how do we actually get an alpha? Do we not care about that? Is it just a matter?
Oh, it's So you just set it to. It's a setting that that you choose, and it's something that if you are trying to optimize the performance of a system, it's something that you should experiment with.
So it's experimental.
So it's experimental. So you just try a half, and you evaluate the performance, and if the performance is not good enough, you try maybe a third or maybe 2/3 and see which one gives better performance. So it's experimental. Yes?
Is it better to overestimate or underestimate the burst time?
Well, that's a good question, but I don't think it's. We will see how the system will be using the CPU burst, but I don't think any has an advantage over the other. I think it's just you just try to make the most precise estimate, because if you underestimate, then it will be good for that process. So you will be favoring that process, because as we will see later, shorter CPU bursts will get higher priority. So you'll be fair to that process, or you'll be biased, in fact, to that process. But if you overestimate, then you will be giving that process lower priority. time.